like as close to your car as you can. And this can go in your pocket or on your belt or wherever.
Yeah, I already have children, so it's not a problem.
Okay.
Where has our director gone off? There he is. Okay, good.
I just put this for you.
Oh, thank you, thank you. You're so considerate. I'm also honored that you know me.
What's that?
I'm also honored that you know whom to give it to.
We have our second director here,
How could I
Joe
forget?
Kaczynski. Here he is. He's in charge. You know, if it's the temperature, you complain to me. If it's the lecture, you complain to him. Joe's giving a public lecture on Wednesday. I saw the ad in the paper yesterday.
Looking forward to that.
Yeah, okay.
Anyway, I read all your applications. I have no idea, though, which names go with which faces. I'm looking forward to getting to know you all.
And, well,
That's fine.
and by the way, we have a lecture today.
Okay, so for the first of his 4 lectures, I guess.
4 lectures here.
First of today, Nati Seiberg, with supersymmetric gauge theories.
Thank you. It's a pleasure to be. Is the sound okay? I hear myself back. It's something wrong with it. Okay. So it's really a pleasure to be back here. I understand that there hasn't been a formal TASI school since the last time I was here. And I'll probably be here in all the next TASI schools if I'm invited. So the purpose of these talks, I asked a little bit about your background, and I understand it's kind of diverse. And so the talk, I will probably undershoot, and I will talk too low a level. And I don't think it's necessarily bad. Even if you heard it before, it won't hurt you to hear again. But if you really find it offensive that the level is so low, please interrupt me with questions. I did not give references in the wiki page. Instead, I put 2 sets of lecture notes that I wrote in the past with Intriligator. In the school I talked here last time, I more or less followed one of these sets of notes. And they're given from 2 different perspectives, although there's a lot of overlap. And I'll do the same thing here. I'll follow the logic of the second set of notes. So if you want any references, these are 2 lectures I wrote with Intriligator. If you just search for Intriligator in lectures, you will find them. And one is, I think, 95, and the other maybe 07. So they are, and they're also in the wiki page. The other general comment, I'm not going to be careful with references. References are for reviews or for books. Here I'll try to emphasize the coherent structure rather than to follow the historical order, which is often quite different than the more logical order that comes out later. So the motivation will be to study supersymmetric. So what I'll be doing will study supersymmetric theories, and I'll do that by examples rather than giving you general rules about how to think about it. And each example will teach us something, and the examples will be progressively more sophisticated, and they will teach us more and more lessons. But there are many misconceptions about these supersymmetric theories that I would like to clarify right now, and then I'll emphasize it again later. So originally, people thought that supersymmetric theories are kind of very esoteric, and therefore they're not interesting. That might still be true, that they're esoteric. Then there was the interest in them for phenomenology, for model building, for solving the hierarchy problem, perhaps for physics at the TeV range. That might still be the case, although the odds are gradually, that would be the case, are gradually shrinking. But in the meantime, it turns out that these theories are extremely interesting for other reasons. This is, by the way, a very common thing in physics, that you sometimes find something interesting in the wrong context, and then first you have to discover it and then find the right context. So this might be another example of that. There are many other examples. So the interest in them became because one can solve them exactly. And I really, really want to underscore here something very, very important. When we say solve them exactly, what we really mean is solve a tiny, tiny fraction of the objects of interest. So you've heard a lot during the last few years. Some of them you might have heard more, or others, about various computations that people do in these theories, for example, computing various indices, various sphere partition functions, omega background, all sorts of fancy things, and people describe that as if they solved the theory. That's not true. They computed one observable, maybe an interesting observable, but it's one observable. And there are a handful of observables that are computable. And then the strategy is always find those observables that you can compute and extract qualitative lessons from these observables. This is really far, far short than completely solving the theory. And this is a misconception that I think should be really clarified and stressed. So there are a lot of examples by now of various theories that can be analyzed and solved in the sense that I've just mentioned. But what I'll do in these talks, I'll primarily focus on n=1 supersymmetry in 4 dimensions, the extensions to extended supersymmetry. Different number of dimensions is interesting. It's kind of more current research, but I would say very little about it. And in the last talk, if I have time, I'll talk about 3 dimensions, and I'll then say why this is a particularly interesting set of interesting dimension to study. So I'll first give you the bottom line. The bottom line will be that there's really one principle that allows you to analyze these theories, and it comes in various different disguises and with different names, and I'll go through that later. So the next paragraph is the summary of all the 4 lectures. So the first lesson, again, is that some observables are exactly computable, and this comes under various different names depending on the historical context in which it was first discovered. It comes under the name of holomorphy, BPS, index, chiral quantities, topological quantities, localizations, and there are many other names. And the common thing in all of them is that some observables in these theories, in these supersymmetric theories, are invariant under half the supercharges, or maybe a quarter of the supercharges, or maybe other fraction. And this fact gives us a lot of control over them. And again, I emphasize this is a tiny fraction of all the observables there are. So this is lesson number 1, which is kind of more of a technicality, because this is the technical tricks that allows us to compute. There's nothing fundamentally deep in the fact that some observables are easier to compute than others. What I think is deeper is the role of duality. And I think this is still one of the most surprising things in modern quantum field theory. And the word quantum is important here, and the word field theory is important. This is an intrinsically quantum mechanical phenomenon. It cannot be seen within perturbation theory. It cannot be seen within classical field theory. And we are constantly surprised by it. And the fact that we are surprised by it, I think, is the sign that we don't really understand it. Because when there's something you understand, you're not surprised by the answer. If you have a symmetry in the problem and you did 2 computations and they are the same by the symmetry, say that's not surprising. When you do the same computation 2 different ways, you get the same answer without a logical explanation, you're surprised. So this is, I think, the sign that we do not yet fully understand duality. So this was the summary of my talks. And I'm going to start now very easy from the beginning. And as I said, I'll be in 4 dimensions. And I'm going to start with the field theory that has only chiral superfields. I assume that everybody here knows about the basic supersymmetry at the level of the first half of Wess-Zumino. Is this true? Yeah. Who doesn't know the first half of Wess-Zumino? And who does know the first half of Wess-Zumino? Okay. And the rest? Okay. So we have a theory with chiral superfield. It doesn't matter what the Kähler potential is, so there's some K. We don't care about that. And there's a superpotential, which I'll call 3. This is what appears in the classical theory. And it has a quadratic term and a cubic term. And this model is known as the Wess-Zumino model. So strictly speaking, as a 4-dimensional field theory, this theory does not exist. It does not exist because if you write it in components, there's a scalar potential which is quartic in the scalar fields, and there's some Yukawa coupling coming from this term. Both the coupling constant G is not asymptotically free. So as we go to higher and higher energies, it becomes stronger. And the law, which is supported by a lot of evidence, is that there is no UV fixed point that can justify studying this theory. Yet this is a very interesting theory. We can view it as an effective theory at low energies. The problems that this theory faces are only at very high energies, exponentially large energies, exponentially large in G, and therefore we can still study it. Also, a lot of the analysis we'll do will be equally valid in fewer dimensions, where this theory is a very interesting theory and it does exist. So this is a general comment about the theory. And the main trick that we will be using is to view, which are complex numbers, but we will view them as classical background chiral superfields. So let me explain that. So imagine we take this field theory and we let M vary in space. So that's not a big deal. We just put M of x here. And similarly, we make G depend on x. So M here in Boulder is a little bit larger than, say, in Santa Barbara or in Princeton. So it can depend on x. And we can describe it as a classical field varying in space. This is a standard trick in field theory to say that the coupling constants are really background fields. They are classical in the sense that in the functional integral, we are not going to integrate over them. We are only going to integrate over the dynamical field phi. Now, the new thing in supersymmetry is that we have these odd coordinates, theta. And therefore, we are going to view M and G as not just classical fields, but as classical superfields. And since they sit in the superpotential, they should better be chiral superfields. So we have in mind having some expectation value or some value for the fermionic component and even the theta square component of M, and similarly for G, and they depend on where we are in space-time. In the end of the computation, we're going to set these guys to 0, so it's not going to affect the answer, but temporarily we can think of them that way, and that, as you will see, give us a lot of power. The second element we're going to use are various symmetries. So we are going to use 2U1 symmetries. One is an ordinary symmetry, under which phi has charge 1. And the other symmetry is an R symmetry. This is a symmetry that does not commute with supersymmetry. And my convention is such that the superpotential has R charge 2, or the supercharge has R charge 1. So this is, again, a global symmetry, and we can act on phi. And we can put any number we want here, because we can always combine an R symmetry with an ordinary symmetry to find another R symmetry. The converse of that is not true, because an ordinary symmetry commutes with supersymmetry. This one does not. So if we add to it anything that commutes with supersymmetry, the commutation is still the same, but the reverse is not true. So we assign a number 1 here. Now these symmetries are not symmetries of our problem. If we didn't have the superpotential, they would have been a symmetry. But the superpotential explicitly breaks the symmetry. Explicitly in the sense that it's not spontaneous breaking. The Hamiltonian does not have the symmetry, and not even the ground state. Later we'll discuss spontaneous symmetry, which is the case when the Hamiltonian or the Lagrangian has the symmetry, but the ground state does not. Here, this is not a symmetry of the problem. However, if we assign transformation laws to M and G, it is a good symmetry. So here we'll put -2, and here we'll put -3, such that these terms are invariant. And here we'll put 0 and -1, so that each term in the superpotential has R charge 2. So we assign charges. So what does this really mean? Whenever we have a system, whether it has a symmetry or not, and whenever we have some transformation on the dynamical fields, we can always promote it to a symmetry by assigning appropriate transformations to the coupling constant of the background fields. This is very common in quantum mechanics. When you study the Zeeman effect or the Stark effect, put the hydrogen atom with its rotational symmetry, say in an electric or magnetic field, and the magnetic or electric field break the rotation symmetry, but the vector of the electric and the magnetic field is a vector in space, and therefore we get selection rules on correlation functions or selection rules on amplitudes and various transitions using the symmetry, even though the symmetry is not there. I hope this is familiar to some of you. So we'll do the same thing here. We assign these transformation laws to M and G such that this is a good symmetry. So now I'm going to use 3 rules, and everything will follow from these rules. The first, I'm going to use the symmetries. Second, I'm going to use holomorphy that I'll soon explain. And 3, I'm going to use various limits. So I'll apply the 3 rules. So my goal is to find the effective superpotential. So we integrate out everything. We go to low energies, and we ask ourselves, what's the low energy effective superpotential? So what should it be? Well, it should be some function of phi, m, and g. But these are complex numbers, and yet the superpotential cannot depend on phi bar, cannot depend on m bar, and cannot depend on g bar. The fact that it cannot depend on phi bar is already in Wesson-Bagger. The superpotential is a function of the chiral superfields, no anti-chiral superfield. The fact that it cannot depend on m bar and on g bar is not in Wesson-Bagger, but it does follow from our philosophy that all these coupling constants are background fields. So if we let them depend on space and on theta, and these are chiral superfields, the superpotential can depend only on m and on g, which are chiral, but not on their complex conjugates. This is principle number 2, holomorphy. Now we're going to restrict this thing by the global symmetries. So we write things that have the right symmetries, and it's easy to see that the most general thing that we can write is m phi square. Well, that's already invariant. That's already in the superpotential in the tree-level problem. So that's already a solution. And the most general solution is some function g of a parameter I'll call t, which is g phi over m. There's only one combination. We have 3 objects in this game, phi, m, and g. We have 2 symmetries. Therefore, there's only one combination which is invariant under the symmetries. And this is it. So far we haven't done any computation, but we did show that the effective superpotential, we reduced it from a function of 6 real functions, 6 real variables, first to 3 by holomorphy, and then to 1 by the symmetries. So this is principle number 1. And now I'm going to use principle number 3 and say, what do we know about this g? So let's work in perturbation theory. For g equals 0, we should recover the classical answer, m phi square. For infinitesimal g, the classical answer is right. So this is just a term linear in t. So we can write here 1 plus, and there is a t, and we also know the coefficient, because the coefficient comes from there. Now, there could be higher order corrections, higher orders in g. But the corrections come from higher tree diagrams. Let's draw such a diagram. You can check that we have a g in each vertex. So this is a diagram of order g to the 4th. We have 1, 2, 3, 4, 5, 6. So we have this gives phi to the 6, g to the 4th, and the appropriate power of m, which I guess would be 5, 4, whatever power.
Nati, I missed something here. This is a Wilsonian effective action, not a 1 pi effect.
I'm going to say a lot about it.
So you're going to say good.
I'm going to, so far I'm deliberately careless. I'm going to be much more precise. And yeah, I use the words very carefully so that I will not say something I don't believe in. At the moment, we are careless about that. And so, okay, since you asked the question, I'll say a few words now, and then I'll say much more. In the textbook that I learned when I was in school, we learned about the effective action. You couple sources, you do the functional integral as a function of the sources, and you perform a Legendre transform with respect to the sources to find what is known as the effective action. This is the 1pi effective action. Such a graph should not be included in the 1pi effective action. It should not be included because these lines, if I just cut it here, it's one particle reducible. So that's already in the textbook. There is another notion of effective action, which is the Wilsonian effective action, where we integrate out the fields, phi. We do not integrate out m and g, but we keep a cutoff. And here the cutoff is in the infrared, not in the ultraviolet. So we integrate out everything above a certain a certain energy, and we write a Lagrangian that the low energy observer could use. In this context, I would like to recommend Polchinski's paper about the Wilsonian renormalization. This is where I learned this stuff. So we put some cutoff, we integrate out everything above that. We do not integrate out the things below. And therefore, such graphs might be present provided this line carries high enough energy. So in the Wilsonian action, it will appear. However, for the superpotential, that's not the case, because for the superpotential, everything, all the external legs, we put all the momenta to 0, and therefore, all the intermediate lines, also the momentum is 0. And therefore, it should not be included in the Wilsonian action. So for this particular problem, there isn't really a difference, and this graph should not be included. So these terms are not there. What about loop diagrams? For example, this one. This one has, let's compare this with that. They have the same number of external legs, therefore the same number of phi's, but this one has 2 more g's that this one does not have. And therefore, it does not respect our functional form. And therefore, all these guys do not contribute also. Now, if you look at the proof, okay, this is what is known as the non-renormalization theorem. This is what is known as the non-renormalization theorem, and the original proofs of it depended on details of writing Feynman diagrams in superspace. In fact, the original ones were actually in component, were not even in superspace. And they were kind of complicated because there were many things you had to rule out. If you look at what is actually being done there, it's precisely implementing these rules. But it's all dressed up in the formalism. So when they say, well, here we must have this vertex, we must have a phi, and therefore in this vertex we have a phi star, and so forth, it's nothing but implementing these rules. But as always, if you find the right symmetry, it's much easier to implement it than to implement various complicated rules. So this is the non-renormalization theorem, and I'm going to make a long list of comments on that. First of all, I proved it here for the minimal Wess-Zumino model, where the interaction is only phi square or phi cube. I leave it as an exercise for you to do it for an arbitrary polynomial interaction. In fact, the more advanced problem would be an arbitrary polynomial interaction with an arbitrary number of fields. So you can write an arbitrary polynomial there with arbitrary number of fields. This thing will still be true. You will have to work a little bit harder, but still remember implementing these rules. Second, you could also rule out these higher order terms that I ruled out by saying they are not one particle reducible. Imagine you did not know that the higher order terms could come from a diagram. So, because the system is very complicated, it's all non-perturbative, you don't know where it's coming from. A higher order term here could be of the form that I wrote before, like this one. We'll necessarily have m in the denominator. So this is the only way to get terms without m in the denominator. This means that if I send m to 0, the answer is singular. That's not physical. And that's easier to say in the Wilsonian language than in the 1PI language. If we send mass to 0, some intermediate particles could still go there, but these diagrams, when the particles are light and they have low momentum, do not contribute to the Wilsonian effective action. Because these are massless particles. When the massless particles being on shell, we do not integrate them out in the Wilsonian term. So another way of saying that these terms are not there is just by demanding that the Wilsonian action is regular as m goes to 0. This is a general principle, and you might have seen that in other contexts. I do not know how many of you learned about Cairo-Lagrangian for pions. Have you studied that? I know that Joe did. Excellent. So if you look at pion-Lagrangian and you compute various processes, there are logarithms of momentum, and there are terms which are analytic in momentum. Similarly, there are terms that are analytic in m pi, and there are terms that are logarithmic in m pi. The terms that are logarithmic in m pi, or in the momentum, they come from infrared physics. Physics that should not be included in the Wilsonian action. This is physics that a low-energy observer will later compute using the effective action, using the Wilsonian action. The terms that are analytic in m pi, where we can set m pi to 0 and get a finite answer, these terms should be present in the Wilsonian action. Right? So similarly here, the action must be holomorphic in m, including at the point m equals 0, and therefore these terms are absent. Next comment, nowhere in this argument did I have to say anything about perturbation theory. The argument is equally valid non-perturbatively. Now one might say that this theory doesn't really exist non-perturbatively, but this is a technical thing and it's irrelevant because, for example, we could study this system in 3 dimensions where it does exist non-perturbatively, and there are no non-perturbative violations of this principle. We will later see that there can be non-perturbative violations of this reasoning, but it comes in a more sophisticated and more interesting way that do not apply here, and I'll explain it in a lot of detail where this comes about. I would like to summarize that as a principle, which I will refer to often in these lectures. I'll call it the no miracles or the no magic principle. In quantum field theory, I think it was Gell-Mann who said that everything that is not explicitly forbidden is allowed. There is a diagram that you compute, there's no reason for it to be 0, then it's non-zero. There is a process that can take place, there's no reason to exclude it, it takes place. That's not the case here. And for many years, it was very puzzling and very surprising. We have the symmetries of the problem, and we have this non-renormalization theorem that tells us that various things don't happen. Well, the general principle is still correct, the no magic principle. You just have to view it as a consequence of more things. It's not just symmetries, but it's a combination of symmetries, holomorphy, and the limits that run the show. And then you can exclude various things that are otherwise allowed. I'd really like to emphasize that if when we use these arguments, if we cannot exclude something, then it is present. So this is the strong form of this no miracle principle. If there is no reason, not just by symmetries, no symmetry based on this extended reasoning to exclude a term, such a term is present, and we'll see examples of that later. So I'll come back to that often and more and more. And the last thing I want to say here is that we can consider a generalization with several fields. Some of them are heavy and some of them are light. In this case, we integrate out, in the Wilsonian sense, all the high energy modes, but also the heavy mode. So the low energy theory includes only the light particles, not the heavy ones. in this case, the non-renormalization theorem is not true. In this case, I cannot exclude such diagrams. And in this case, I cannot exclude terms where mass appearing in the denominator. From the Wilsonian point of view, I go to energies below m. And if I'm at energies below m, nothing stops me. In fact, I'm instructed to integrate out these massive particles. And when I integrate them out, I can get m in the denominator. But still, life is quite simple. Such diagrams do contribute. They do renormalize the superpotential. The effective W differs from the tree-level W. But they differ by terms that can be computed classically. So it's just looking for the stationary point, solve the fields, and plug it back in. We'll have a lot of examples of that later. Any questions so far? Yes. I thank Eva for slowing me down, and I'm disappointed that not more people slowed me down. Thank you, Eva. So we'll have a theory with two fields. A light one, m, ml square, and a heavy one, m, h square. And big M is bigger than little m, because it's heavier. And these two guys couple to each other. So imagine there is a G L square H. So this is our tree-level Lagrangian. There are diagrams What did I do wrong? There are diagrams like that. And such a diagram should not be included at any, and we are interested in the Wilsonian action at energies well below m absolute value and well above little m absolute value. So such a diagram should not contribute, because from this propagator we're going to get 1 over little m. So such a diagram does not contribute. But what about such a diagram? At these energies below big M and above little m, we should integrate out the heavy guy. We should integrate out the heavy guy, and we should include such a diagram in our reasoning. So we either compute the diagrams, or you go from here and you look at the equation of motion of the field H you integrate out. So we're going to get 2mh plus GL square, and we set it to 0. And I made a mistake. That's the whole point. I hope I didn't mess it up. So we can solve this equation. And substitute it back in here. Well, this gives me a minus sign, and this would be a square, and this would be a fourth, and this would be a 2m, and that has the effect of making it a minus sign here. I hope I did not make a mistake in the algebra. So now, notice what happened. The reasoning of the non-renormalization theorem is still valid here, but it's not equal to W3. It's obtained from W3 by solving the equation of motion of big H and substituting it back in. In terms of diagrams, this is the statement that we integrated out the field H, and this diagram produced the L to the fourth term. Does this answer your question, Eva? I think the language of what's tree and what's not tree can be used, and it's helpful, but there are situations where it's not available. And when it's not available and it's not clear what you integrate out and what not, I think we should still use these rules. So if we just tried to use these rules, what would we have found? We would have found that we are looking for an effective superpotential, which is a function of, in this case, without H. We want to integrate out the field H. In this case, we'll use the same reasoning, right? The most complicated, the most general thing we can have. Go to weak coupling, use holomorphy and the symmetries, and you will see that there are two terms that can be present, these two terms, and no other terms can be written. No. Well, I drew the diagram and you saw that it could not. I'm happy to do the arithmetic. So I'll give you three answers. Well, four. First, take it as a problem. Second, in order to produce another diagram, you see every diagram will have something like this, and there will necessarily be an L in an intermediate line, and therefore there cannot be another diagram that can contribute. And finally, we also did the computation. We integrated out at tree level exactly. What this computation shows, this is completely equivalent to doing the tree level computation. It's easier than the Feynman diagrams, because you don't need to know Feynman rules in superspace and all that. You just differentiate with respect to H, and you find that. And there's no higher order term. That's right. So that's the reason I hesitated before I wrote this term. So that, yeah. But again, there could be more terms. It might be more complicated. In fact, thank you for asking. Take this problem and write the most general answer. There's a simple closed form formula where there will be higher order terms, exactly like the terms that you ask for. But the problem is still exactly solvable, and you'll get a much more complicated answer. Thank you, Joe. So this is all I wanted to say about theories that do not have gauge fields. And before I go to gauge fields, I'd like to ask whether there are any other questions. Please ask me questions. Please, please, please. How many of you have already heard that, what I've said? Most of you. So that's why there are no questions. So can I speed up? No. Where are my notes? I have enough material here for as many hours as you want. So for me, it doesn't matter. So we add gauge fields. And I'll first do it classically. And the prototype example I'll be studying is SUSY QCD. This is an SU NC theory, which has NC for colors. And it has NF flavors, which are quarks in the representation n plus n bar. I'll denote these by q's and these by q tildes. And I'll not put a bar over q because I reserve bar for complex conjugate, and q tilde is not the complex conjugate of q. It's another chiral superfield. The complex conjugate of q is q bar or q dagger, which is an anti-chiral superfield. And if you look at Wess and Bagger, this will be challenging here. Okay. If you look in Wess and Bagger, you will find that there is a potential, which is the sum over the generators of the gauge group, dA square, So star is the complex conjugate, dagger is including transpose, which I'll define in a second, dA Q tilde transpose, and all this is squared. So this is dA, where the Q's and the Q tildes are matrices which have color index, color running this way, so called I equals 1 through NC, and flavor index running this way. So if you substitute it in and if you view them as matrices, the TAs are the generators of SUN, they give you this formula. So our first goal is to use the classical problem and ask, when does the potential vanish? Again, I would like to make a point that you'll probably fully appreciate later. It's very common among young people today to go ahead and run with the quantum theory, not thinking about the classical system before. And it's a general rule that understanding the classical system before you jump into the quantum system is a good idea, because many things can be understood classically much better. And you're not like, there are many pitfalls in the quantum theory that if you didn't get the classical story straight, you will fall into. So I can assure you that you will face this lesson later in your life. So we're looking for solving these equations. These are matrix equations. We're looking for solutions, V equals 0, or equivalently, dA equals 0 for all A. So I'm going to divide that to several different cases, depending on how many flavors and colors we have. So imagine first that the number of flavors is less than the number of colors. And then it's easy to show that the most general solution up to symmetry transformations, which I'll define in a second, is of this form. So the Q's are rectangular matrices. They have more columns than rows because the number of flavors is less than the number of colors. Using unitary there are 3 unitary transformations that we can act with. Flavor acts from the left, color acts from the right here. So there's a theorem that every rectangular matrix can be diagonalized by a bi-unitary transformation, one unitary transformation from the left and one from the right. So with Q, we can always bring it to this form. And with Q tilde, we can no longer bring it to this form using the symmetries, but then the equations easily show that this is the most general solution. What happens classically? Classically, we had an SU NC gauge group. So let these V's be generic numbers. So if they're non-zero and color acts this way, then the first block is non-zero, and the remaining gauge symmetry is only the transformation acting on the remaining column. Therefore, we have a phenomenon of the Higgs mechanism. Where the gauge symmetry is Higgs down to a subgroup, SUNC minus NF. So again, we ask ourselves, what are the light degrees of freedom, the degrees of freedom that later will integrate out the rest and find an effective Lagrangian for them. So again, we have what is light and what is not light. So we have in mind making these V's large and generic. And as far as the gauge symmetry, we started with that. We end up with that. So the low energy observer sees only this unbroken gauge group. The low energy observer also sees other degrees of freedom associated with changing the values of V's and maybe acting on them with various global symmetries. A way to parameterize it is to define a meson field. It's Q tilde Q transpose. This is in the matrix notation, or in more explicit notation, Q tilde A tilde I Q I A, where this is the color index, this is the flavor index of Q, and this is the flavor index of Q tilde. They transform under different global symmetries. Then I cannot write. Is this good enough? So I claim that the most general solution, so a low energy observer sees SU NC minus NF gauge theory and NF square fields M. Let's do the counting and make sure that we got it right. How many Qs we started with? Started with 2 NF and C chiral superfields. These are these Qs and the Q tildes. There was a Higgs mechanism. How many of them were eaten? Well, we started with SUNC minus 1 gauge fields. We subtracted those that remain. Thank you. Only if I get a bigger chalk. Here is a bigger chalk. Is it big enough for the people at this end? Because it's not that I move to this side so that Joe can see better. So we started with how many fields? This is the dark side. Can you see the dark side? Not well. Thought there would be some Star Wars joke, but there wasn't any. So this is the total number of chiral superfields we started with, eaten in the Higgs mechanism, whatever we had before. So these are the number of gauge fields in the original theory. These are the number of gauge fields that remain light. The difference between them is the number of gauge fields that were eaten, that got a mass. Every vector superfield ate one chiral superfield. So out of these, this difference we subtract. And the bottom line is that we end up with NF square M's. These are the M fields. So this shows that we really have all the light degrees of freedom that we should have. They also represent all the global symmetries, because this M matrix M transforms under the full global symmetry, SUNF times SUNF. So a low energy observer sees a nearly decoupled gauge sector and a nearly decoupled theory of M of these chiral superfields M. And what the next thing that this observer will have to do is to compute their effective Lagrangian, integrate out all the heavy stuff. Now, things are getting a little bit more interesting if we have more flavors. Repeating the same reasoning as before, we can bring the matrices to this form. So without loss of generality, we can diagonalize this one. So now we have more flavors than color. And now we try to solve the D-term equations. The equations I wrote there. And the most general solution is V1 tilde, V2 tilde, V and C tilde, and zeros here. But the fact that these two guys have to be equal, at least in absolute value, is no longer true. We have more general solutions. And we can have Vi square minus Vi tilde square is independent of I. This is the most general solution of the equations. So what does the low energy observer see? The SUN gauge theory is completely Higgsed. So the low energy observer sees only some chiral superfield that represent the solution of these D-term equations. And we should be able to describe it using such gauge invariant polynomials like this M that we mentioned before. So what can we do? We could still use the same M that we had before. Where was it? Here. Q tilde Q transpose. This is a matrix. Call this a meson. But we can also form some baryons. And similarly, B tilde with epsilon and Q tildes. So here the terminology is that these are baryons and these are antibaryons. So that's a lot like in ordinary QCD. The meson M is QQ tilde, a quark and an antiquark. And the baryons are made only out of quarks with an epsilon tensor on their color indices. And because of Bose statistics of the superfields, we have epsilon tensor, we have antisymmetrization of the flavor indices. And these are antibaryons. We couldn't do that with fewer flavors, because with fewer flavors, the color index has to be totally antisymmetrized, but then the flavor index has to be totally antisymmetrized, but we don't have so many of them. Now, there's a general theorem from 19th century mathematics that I'm not going to prove here, which does something that we've already demonstrated here, but I'm going to state it more generally. It's called geometric invariance theory. So these mathematicians were interested in solving precisely these D-term equations. They didn't formulate it in this language, but that's exactly the set of equations that they wanted to solve. We have a gauge group in our language. We have a gauge group. It doesn't even have to be SUN, acting on some, in general, reducible representation of the gauge group. For us, it's this fundamentals and anti-fundamentals. And the space of solutions of these equations, modulo gauge transformations, is exactly the same as the set of gauge invariant polynomials we can write out of these Qs. And again, we are not allowed to use complex conjugate. We are only allowed to use the holomorphic quantities. So it's exactly what we need. Take all the chiral superfields, no anti-chiral, write the most general gauge invariant polynomial you can write out of them. Since it's gauge invariant, you no longer need to mod out by the gauge group. And the space of solutions is parametrized by these fields. In the first example of NC less than NF, everything is parametrized by this square matrix M. And we did the counting to show that it works. And with more flavors, it's a little bit more complicated, because we have more gauge invariant things we can write down. But in fact, things are even more complicated, because if you count now how many fields were eaten, NC square minus 1 were eaten. You ask how many we started with. It's not that different than the counting we did here. But if if you just add all the degrees of freedom here, here, and here, you'll see that you have too many. You have too many. So that means that these guys are not independent. We have overcounted them by representing them this way. Where did I write the most general metrics? This is the problem with moving blackboards. I can never remember where. Oh, here it is. So look at these matrices. And note that the rank of the matrix M is at most NC. Just take these solutions, form the matrix M, and you will get an NF by NF matrix whose rank is at most NC. So even M does not have the full NF squared degrees of freedom it could have. There are some relations between them. And in this case, it's relatively easy to write the relation that the rank is restricted, but not all the degrees of freedom are independent. Furthermore, there are relations relating M and B. So for example, let NF be equal to NC. So now there is only one B, which can be written as the determinant of Q. And there's only one B tilde, which can be written as the determinant of Q tilde. And we have our friend M, which is Q tilde Q transpose. Now again, I'm going to use a theorem from mathematics, but this is a theorem that you all learned before. The determinant of M is the determinant of this. It's the product of the determinants. And the product of the determinants is precisely B times B tilde. So in this particular case, this is the only relation. Let's do the counting. Square fields. These are the Q's and the Q tildes. Eaton the gauge group is completely broken. And when we subtract, we are left with NF squared plus 1. So M has NF squared degrees of freedom. B gives another one. B tilde gives yet another one. But we subtract 1 because of the constraint. Would like to emphasize again that I'm not doing anything fancy here. I'm just doing classical physics. What quantum mechanics is going to do to all that will be very interesting. But at the moment, we are just studying the classical theory. So here, I'll denote it by M classical. I'll soon define it. It's the space of all M's, B's, and B tildes such that M equals B tilde. This is a space. And this is the space of classical solutions of this is the space of classical solutions of these D-term equations. These are the classical ground states of the system. So we say that the system has a classical modular space of vacua. Semi-classically, so I'm using the quantum language, but for the classical theory, we can formulate a theory, pick a value of M, B, and B tilde, such that this equation is satisfied, or equivalently, pick a point here in this space, up to the symmetry transformation, and start writing the light degrees of freedom, work out the interactions around them, describing the low energy physics around this point. So this is the modular space of classical ground states. What happens quantum mechanically? Well, the first thing to compute is perturbation theory. And thanks to the non-renormalization theorem that we proved before, not much happens in perturbation theory. We can repeat the reasoning that we used for the Wess-Zumino model in this system to show that this vacuum degeneracy persists to all orders in perturbation theory. This is something that is very common in supersymmetric theories. not common without supersymmetry, but also common in supersymmetric string theories. We have a modular space of vacua, and they are inequivalent. Without supersymmetry, there is no non-renormalization theorem, and therefore this vacuum degeneracy is typically lifted. You can start classically with two states. You have a potential which has two vacua, and for no good reason you tune two of them to be exactly equal. This is called an accidental degeneracy. There is no symmetry between them. Quantum mechanically, the radiative corrections on one side will not be the same as the radiative corrections on the other side, and this vacuum degeneracy will be lifted. So if there is a symmetry guaranteeing it, the vacuum degeneracy persists, and this is the phenomenon of spontaneous symmetry breaking. In this case, we have vacuum degeneracy without a symmetry protecting it. So this is what happens classically and in perturbation theory. So to summarize again, we have an SUN gauge theory with some matter fields, chiral superfields in the fundamental and anti-fundamental. Found a large space. It's quite complicated space of classical solutions. And to all orders in perturbation theory, this qualitative picture remains true. So the next thing I'm going to discuss is what happens non-perturbatively. Any questions so far? Well, in general, it's not true because there are interactions and all sorts of things can happen. Here, I'm basically doing the classical analysis. So every field that was lifted, it's an equation that we solved. It's like saying how many equations we have, how many unknowns. These equations are more or less linear. So we just subtract number of equations from number of solutions. In the quantum system, relating the number of degrees of freedom at short distance and the number of degrees of freedom at long distance. So that's what we did here. We started short distance with some number of gauge fields and chiral superfields. We ended up at long distance with these M's and B's and some non-abelian gauge theory and so forth. And the difference between them is, so first of all, we have more degrees of freedom at short distance than at long distance. And the difference are precisely these fields that became massive through the Higgs mechanism. In more interesting systems, or when we add interactions, could be more complicated dynamics. Some of the degrees of freedom will be confined. All sorts of things can happen. But the law is that at short distance, we have more degrees of freedom than at long distance. And I use the word law and not theorem because I just use the imprecise statement, number of degrees of freedom. A more precise statement is known in 2 dimensions as the C theorem. In 4 dimensions, it's known as the A theorem, which was written. So C theorem was proven by Zamolodchikov long ago, and the A theorem was proven recently by Komagotsky and Schwimmer. And the general rule is that as you go to the infrared, there is thinning of the number of degrees of freedom. There are fewer degrees of freedom. And we see here a demonstration of this. This is a very trivial demonstration. In fact, we saw a demonstration of that already in the system that Eva wanted to know about, with one heavy and one light field. At short distance, we had 2 superfields, H and L. At long distance, we have only one superfield, L, because H was integrated out. So we see again this inequality, but it is in a kind of trivial sense. The theorem is a lot deeper than this trivial sense. There was another question here? Yeah.
Yeah, I'm confusing myself with these baryons. In QCD, when you have just 2 flavors and still form
QCD is a lot different than that, because first of all, you make them out of fermions. And here I'm doing the superfields. So it is as if I'm combining the scalars. So that's the first thing in the thing. Second, since it's fermions, there's spin. And third, you can also have angular momentum. So maybe in the simplest baryons, this doesn't happen. In here, it would correspond to throwing in a derivative, 2 derivatives. But yeah. And it also has, overall, it has spin a half, and here it has a, yeah. Thank you for the question. How much time do I still have? 1:15. Okay. And way behind my schedule. So we're going to discuss now the non-perturbative system. And And this can be done in many different ways. And this is, again, common in dualities, that every system can be analyzed in many different orders, as long as, and we often find the same answer by doing it in different orders. So I'm going to start by stating some facts about the theory without matter, just a pure gauge system. And then I'll add the matter fields, but I'll add them with very large masses. And I'll present a solution of the system as when in the limit that the mass is very large. This will be relatively easy. And then the fun will be when we'll study the same system in another limit where the mass is very small. And we'll see how we reproduce the same answers, but with a totally different physical interpretation. So that's the order. So I'm going to start with just pure SUNC gauge theory, no matter. So this is a pure gauge system. It has fermions in the adjoint, the gauginos. And it's convenient to define, and again, I'm using Wesson-Bagger notation. So there's a 1 over 32 pi squared. That's just for convenience. The coefficient is not going to matter for us. Trace of W alpha square, which in component means 1 over 32 pi square. Trace. Lambda lambda, that's the gaugino, plus all sorts of terms. We'll also need theta square, f mu nu, f mu nu. And I'll refer to it as the global superfield. Global because it's roughly made out of two gluons. It's like a bound state of two gluons. And I'll say later in what sense we can and cannot think of it as a global field. So this is the classical system. No need to discuss modular space of vacua because there aren't any. There's only one vacuum. There are only fermions and gauge fields. So classically, that's what we see. 1 point. Next thing we do is perturbation theory. In perturbation theory, I'm going to write a formula that I'll come back to again and again. The system needs to be regularized. So I formulate it with a cutoff. Okay. When you studied quantum field theory, you usually you were presented with the logarithm of this formula. You formulate the theory with a cutoff, with a coupling constant g at the cutoff, and you form this combination that is going to be a renormalization group invariant, and you call it lambda. That's the low energy scale. So the physics is, so first of all, the sign here is minus. This is the sign of asymptotic freedom. And the coefficient here comes from the one-loop beta function. The fact that there's a minus sign here was a Nobel Prize for Politzer, Wilczek, and Gross. And so usually this comes with the logarithm. And this theory at very high energies is very weakly coupled. As we evolve to the infrared, at scale of order lambda, things become interacting and interesting. Various glue balls are formed and so forth. All the dynamics is at that scale. And the law is that there is a gap, and below a certain lowest mass glue ball, there is nothing, and we find only the ground state. In fact, I'll be more precise what we find then. I'll find it convenient to define a variable eta, which will be lambda to the 3nc, to remove this factor from here, which will be m cutoff to the 3nc, e to the minus 8 pi square over g square of the cutoff. So this might look like a perverse thing to do. We have a scale lambda. Why should I raise it to this funny power? it will turn out to be a useful thing to do. So now we're going to follow the same logic as with the Wess-Zumino model, and we'll study the symmetries of this problem. There's a U1R symmetry. We have a fermion lambda, we have a global S, and we have this guy eta, which is lambda to the 3nc. So without loss of general, well, in our conventions, the gauginos have R charge 1. Who can tell me the R charge of S if lambda has R charge 1? Good. In the classical system, U1R is an exact symmetry, and therefore this is all there is to do about it. But in the quantum theory, this U1R symmetry is anomalous. And since it's anomalous, the symmetry is not a precise symmetry in the quantum theory. It is explicitly broken. And the mechanism that breaks the symmetry is instantons. An instanton can be thought of as a vertex. Short distance there is an instanton. It looks like a vertex spitting out 2nc gauginos. And every instanton comes with a factor of e to the minus 8 pi square over g square. So this thing is precisely the effect of one instanton. So whenever we have an instanton, we can think of it as a vertex that violates the symmetry by 2nc. I use the language of instantons, but I didn't have to. Even if you never heard about instantons, you did hear about the anomaly. And the anomaly tells us that the U1R symmetry is violated. And the divergence of the current is F wedge F. And F wedge F is the same as the F component here. And if you put all the numbers in, and you put it in the exponent because it's easier to exponentiate things, this has charge 2nc. Another comment I have to make is that when I define lambda like this and m in terms of m cutoff, somebody here in the audience might find it convenient to regularize the system in a different way. And if you regularize the system in a different way, you will find another lambda. So in QCD, there are various schemes that are popular, MS bar and MS and various other things in supersymmetric theories. There are all sorts of good regularizations that people use. I'll use a specific one known as dimensional regularization bar, dimensional reduction bar. It doesn't matter what it is. It is the one where most of the coefficients are set to 1. And I'll say explicitly where these numbers are 1. And even that will not be very important for us. All I do want to emphasize is that so far I've done nothing but one-loop physics. One happens non-perturbatively. I'll formulate it as a law, which I will later prove. So I'm leaving one gap here, which I will later close. But at the moment, I'll just state the fact. This system has confinement. Oops, that's black. That's not big enough. Is this big enough? There is a gap in the spectrum. So that's the law. So far, it's a law. Later, I'll prove it. There is a gap. That means that there is a ground state, perhaps more than one ground state, no light particle, no massless particles, and then at mass of order lambda, there could be all sorts of particles. Let me make one more change here. I'll add here the theta parameter. I'm sorry that I forgot to do that before. And the notation might be confusing. This is theta of theta QCD, not to be confused with the anti-commuting theta that appears here. And I hope it will be clear which one is which. And again, we see here, this is the hallmark of an instanton. E to the minus 8 pi square over g square is the action of the instanton. And it comes together with the instanton phase, with its which e to the I theta. So we continue with the law, is that this S has an expectation value, pi square, Notice that it has the right dimension because here lambda is a complex number. It has dimension 1. So eta has dimension 3 nc, are divided to the power 1 over nc, and such that it has dimension 3, which is the dimension of S. So the normalization, I was very careful with the normalization of S. I defined it precisely. And here I'm giving you the precise expectation value, the precise value including the numbers of order 1. I'll derive this number later. And the scheme in which this is right is this dimensional reduction bar. And the physics of this is that we had U1R classical symmetry. It is explicitly broken to Z 2nc R symmetry. 2nc because this object eta has R charge 2nc. So again, if the parameter has a charge, we can read off the unbroken group. So the unbroken group is Z 2nc. And then there's the phenomenon of spontaneous symmetry breaking. Spontaneous breaking. So the classical system has a U1R global symmetry. The quantum system has a Z2nc global symmetry. And this global symmetry is spontaneously broken to Z2. And when the symmetry is spontaneously broken, we have NC vacua related to each other by the action of this global symmetry. This is the interpretation of the fractional power here. Everything here has to be nice analytic functions of eta, not of lambda, but eta. That's why I defined eta the way I did. Everything should be nice analytic function of eta. So somebody could ask, how come we have a fractional power? That doesn't look analytic. Most precisely, this object has nc different values. There's kind of a phase here, e to the 2 pi I k over nc, with various values of k. What does that mean? It means that the system has nc different ground states, and the different values of k label the nc vacua. So the system has nc vacua labeled by parameter k, and the fractional power here has a good reason. We'll see a lot of it later, that these fractional powers, these things that look non-analytic in the effective action or in various observables, reflect infrared dynamics of the theory. I see that Tom is getting a little bit anxious, so I guess I'll stop. We'll continue in the afternoon. Is there time for question now or not? How does it work? Oh, there's coffee. Are you next, Eva?
Yeah.
Thank you.
Shut up when I haven't gotten any sleep.
No. I'm so happy. I'm so happy you ask questions. I should encourage people. I think I do not know what to do to encourage people to ask more questions. So I don't have my. I told you I lost my glasses, so I have these spare. These are only reading glasses, and when I use them like this to read my notes and look at you at the same time.
You look like a grandfather like you. Where's your baby for all you
No, I'm not.
Not yet.
I could have been, but I'm not.
So this afternoon with the session before, I'm kind of wondering how those have worked.
Hi, how are you?
Good.
I do remember. Relax. I looked at the faces. I know only a few, and you're one of them. I'm sure you know everything I said very well.
It's nice to hear things you already
Yeah, you're always nice. You're always so nice. Say hi to Ken.
Yeah, I will. He says hi to you.
Yeah, I'm going to meet him next week in India.
Oh, yeah, great.
Good. You having fun here? Learning some stuff?
It's great.
What year are you now?
I just finished my second year.
Second year of graduate school? So when I met you, it was after the first year? Ah,
Yes, I've been working on.
do you want to have some coffee?
Yeah, so when I met you last year, I just started working with Ken on this all 40 equals 1 dualities in a species.
Ah, these E7 theories that, yeah. Yeah. You told me about that.
Great. So, yeah, we've been thinking about that for about the last year now. And we're very close to publishing this summer. But
Ah, excellent.
yeah, it's been very interesting.
There was this, what's her name? Lynn, right? She also worked on that. She's coming to the institute.
Yeah,
Yeah, I know. And Ken just finished the paper. Oops, I have to. All this is, whatever you say is recorded.